In the previous video, we examined the forces and energies on the spring mass system. Now let's take a look at their equation of motion and see how we can describe this motion in time and position and velocity and acceleration, kind of those kinematic quantities. I want to start by looking at a graph of the position versus time. So remember in the previous video I drew some sketches of what happens when you stretch the spring out and let it go. Now this graph shows you the stretch on the vertical axis versus time on the horizontal axis. So at the very beginning of this graph, we have stretched the spring out to its maximum amplitude. And then we let it go. So the spring collapses and it shortens and it reaches its equilibrium position here, where x is 0. But then, because that mass has some inertia, it keeps going and it overshoots that equilibrium position, compresses the spring, and reaches that amplitude in the negative direction, to the left. So this is the maximum compression. The spring pushes the mass away because it's compressed. It passes through equilibrium once again. It's going the other way through equilibrium this time, and then returns to the start of that maximum stretch. And then that whole process repeats over and over again. Now, the shape of this graph hopefully looks familiar. It's a cosine function. And we can write a formula for this cosine function. Unfortunately, we can't derive where this formula comes from in physics 6 because it requires differential equations. But it comes from solving Newton's second law for the spring and noticing that because the acceleration is not constant, we have to do some calculus and differential equations to solve it. And the solution is that the position as a function of time looks like this. A times cosine omega times t. So I'll explain what that omega is in just a second. But the first thing to notice here is that this is an equation for the position as a function of time. So whatever value of t you use, you plug it in here and you can calculate a number. We have A, this amplitude, that is multiplying the cosine function. So remember, cosine has a maximum value of 1 and a minimum value of -1. So if we multiply by A, we scale this graph so that the maximum value this can have is A and the minimum value you can have is -A. And t is our independent variable. Omega is called the angular frequency, and it's really similar to the angular frequency we talked about in circular motion. In fact, there's a lot of connections between this back and forth vibrational motion and circular motion that we don't have time to get into now. But omega is called the angular frequency. And it's telling you how many radians of this cosine function are accomplished per second. Okay, we have a formula for omega. It's defined as the square root of k over m. where K is the spring constant and M is the mass attached to the spring. Now we can define another quantity called the frequency, not angular frequency, but just frequency. This one's a little more intuitive than angular frequency is. Frequency is omega over 2 pi. So that's 1 over 2 pi root K over M. And one more important quantity, the period. That is 1 over the frequency, or 2 pi M over K. So let's think about what each of these quantities represents. Angular frequency is telling you how many radians per second of this motion are occurring. One back and forth cycle of the spring is 2 pi radians. So this is radians per second. Frequency is how many complete cycles occur per second. A cycle is 1 back and forth. So this is cycles per second. Cycles don't have a unit, so that's just 1 over seconds. And this is commonly called hertz. The number of occurrences of some event per second. And period tells you how long it takes to accomplish one complete cycle. So how long does it take for the spring to go back and forth once? So we measure period in seconds. All right, so once again, in reverse order, period is how long it takes for the spring to go back and forth one time. Frequency is how many times per second the spring goes back and forth. And angular frequency is how many radians per second of this motion the spring accomplishes. Now on this graph, we can show what the period is, because one complete cycle occurs after a time equal to the period. So there's one complete period. Another cycle happens over here, so this time would be 2 periods. Over here we'd have half a period. 1/4, 1/2, 3/4, 1 period, 5/4, 6/4, 7/4, 2 periods. Now, we can also have equations for the velocity as a function of time, and the acceleration as a function of time. You can derive those from the position function with calculus. Take the derivative. And if you look at these, notice that you can easily read off the maximum value. So the maximum position that this spring can have is the maximum value of this function, which is A, because cosine has a maximum value of 1. The maximum value that V can have is omega times A. And the maximum value that the acceleration can have is omega squared times A. And remember from our previous video, this maximum position occurs when you pull the spring and let it go. The maximum speed occurs when the object moves through the equilibrium point, when x equals 0. And these maximum acceleration values occur again at the same position as the maximum position at the endpoints. All right, let's do one example calculation here. Example 13.6. Let's consider a system that's oscillating in simple harmonic motion. Simple harmonic motion. Well, I don't know if I explained that term yet. Simple harmonic motion means that the system obeys this equation. Any system that is described by this equation, which is not just limited to springs, as I keep saying, it applies to all sorts of things in nature, exhibits simple harmonic motion. Harmonic meaning described by sines and cosines. Okay, so that's simple harmonic motion. And it's described by x as a function of time equals 0.2. I didn't give myself enough room here. Let me try it again. Described by x as a function of time equals 0.25 meters times cosine pi over 8 t. And so the question here is find all of these quantities that we just defined. So find A, omega, F, T, V max, A max. Some of that stuff we can just read off directly, right? So this equation we can see is in the same form as our simple harmonic motion equation. So we can just read off some of these values. The amplitude is whatever is multiplying that cosine out in front. So it must be 0.250 meters. The angular frequency is whatever is multiplying time inside the cosine function. So it must be this thing pi over 8. And if you actually do that little calculation, it gives you 0.393 radians per second. Frequency is omega over 2 pi. Which would be 1 over 16, or 0.0625 hertz, or 1 over seconds. Period is 1 over frequency, or 16 seconds. So we can now see that writing omega this way was a way of saying that the period of the system is 16 seconds. And what else do we want to know? V max, omega A, .0983 meters per second. That's the speed of that block when it passes through equilibrium. And we can also find the maximum acceleration. .0386 meters per second squared. Now there's one more question we might want to ask. what are the values of x, v, and a after 1 second has passed? Alright, so pull that spring back, let it go, clock 1 second on your timer. Where is that block now? How fast is it moving? What's its acceleration? Well, that's what these three equations are good for. You just plug in 1 second for t in each of these and evaluate the result. So plug in t equals 1 second into this equation and these two with our values of omega and a that we found. I'll let you guys try this at home. And you should find, after 1 second, the block is at a position of 0.231 meters. It's moving with a velocity of negative 0.376 meters per second, and it has an acceleration of negative 0.30357 meters per second squared. All right, last reminder. These are the equations of simple harmonic motion. We've been analyzing them for a system of a mass attached to a spring, but this is completely universal. Pendulums do this. Strings on a piano, on a guitar, do this kind of motion. Molecules do this kind of motion when they are vibrating. Those vibrations lead to emissions of light, electromagnetic radiation, that is described by this kind of motion, described by the same math. Structures vibrate in response to a wind or passing traffic in simple harmonic motion. Seismic waves can be described by simple harmonic motion. This is a pretty universal phenomenon. It's not just limited to springs.